Good morning. This is lesson 2 of topic 4. In last lesson, we talked about the structure of an atom. We talked about the nucleus containing the protons and neutrons, and the electrons in the shells on the outside. We looked at how we can write them down by their chemical symbol and their atomic mass at the top, and their atomic or proton number at the bottom. We then did a quick look at ions, which we cover a lot in chemistry, and then isotopes. And isotopes is what I want to focus on today, about how if we have an imbalance of neutrons, that can cause radioactive decay. So radioactivity. It's one of the probably least understood types of science, or misunderstood by the general public. They're fairly oblivious as to really the level of danger. It's not that dangerous. Shows like Chernobyl and large explosions like that give people a disproportionate sense of the dangers of radioactivity. And if you think about it, when comic book writers were coming up with new ways of creating elaborations on the old legends of gods, radioactivity offered a really good way of creating superpowers. So we always imagine, when we think of radioactivity, kind of glowing, mutations, and death, usually. Very rare you ever get superpowers, but I keep trying. So that's what today is. What is actually going on? Who discovered it? How it happened? We'll get rid of these, cut these out. Oh, as fun as they are. Still one of my favourite films, Spider-Man. And so today is radioactivity. And first thing is, we'll have a look at what causes it. So radioactivity is caused by an imbalance of energy inside a nucleus. And that gives rise to 3 main types of radioactive decay. Now, the discoverers of this didn't know they were discovering it, and it was quite by accident. And it was a guy called Henry Becquerel. And if we go over, we can find some photos of him. Here we go. So this is Henry Becquerel. This is taken later on in his life. And Henry Becquerel was an avid geologist, and he used to collect rocks, and in particular, uranium salt rocks. And so one day on a Friday afternoon, he put his rocks in one of the drawers. And his other hobby was photography. And in those days, it was photographic plates. And you keep them in the dark, so the light doesn't expose them. And he put them in a second drawer. When he came back the next day, he discovered that a form of light was somehow penetrating the wooden drawers, going through the wooden box that the plates were in, and some sort of light was getting through. And so he discovered the first forms of radioactivity. Now, he had a partner in all of this, a woman called Mary Curie. So this is when they were younger. And Curie is one of the classes we named a group after a long time ago. And she's one of the few women recognised for her efforts in science. There were many, but most of the times there was a bloke next to her taking the credit. So he discovered it. He got the Nobel Prize for Physics in 1903. And he got the unit of decay named after him, the becquerel. And we'll look at that in lesson 3. Here they are working on radium. Unfortunately, guess what? Both died of cancer, brought about by the amount of radioactivity they were both exposed to over their entire life. So, without further ado, let's have a look at what the 3 types are. They're called after the 3 first letters of the Greek alphabet. So we start with alpha. Now, an alpha particle is a particle that is very large. We must exceed, and I'm not going to draw them. In fact, I'll just draw a ad hoc version. What we're talking here is an atomic number of 80 plus. So 80 protons minimum for this to happen. This happens to the truly large, and if we choose our red and we just dot in a couple of protons, I'm not drawing 80, but get the idea. So these happen to the larger ones. So when you look at the periodic table and you look at the bottom and you notice they're radioactive, it's usually alpha. So let's put these in. There's my neutrons. And so these atoms are so big they can afford to lose whole chunks of their nucleus. So an alpha particle is a proton. Colour that one in. Take a copy. Another proton, bonded like so. And then a neutron. Let's do it perfect. A neutron and another neutron. Copy, paste. I love doing this. And one there, and whoop, one there, and one there. Okay, so it's a clump of matter. This is an alpha particle. And it's shot off with great energy, like so. And it's composed of a proton and a proton and a neutron and a neutron, like so. So we can write that as 2 proton plus 2 neutron neutral. And that means it has a relative atomic mass of 4. It has a charge, because there's 2 protons, of plus 2. And it has 2 things we measure, and I'll explain a little bit more as we go. One of those is penetration, i.e. how far can it go? I'm pretty sure I'm spelling penetration wrong there. Hey ho. Penetrate, I don't know, you're smarter than me, you'll figure it out. But penetration means just basically how far will it go. So in this case, this thing will go about 4 centimeters in the air, and it will get stopped by paper or skin. So actually this one's quite a safe one. It doesn't really hurt you too much. The other thing is ionization. Its ability to create ions because of that plus 2 charge. And because it's the biggest of the 3 and it's the most charged, it is highly ionizing. We'll come back to that more. There's a nice diagram I can show to show that. So that's alpha particles. Next, this one's a little bit trickier. This is beta particles. Now, if we take an isotope, and if you remember, we looked back at isotopes here. Remember, the pink line is a zone of stability. This is the region that goes on the periodic table, so 1, 1, 4, 2, 7, 3. These are the stable configurations. But if you add too many neutrons, then what happens is it becomes unstable and it can decay. And so under here, now if I label this up, I'm going to take a screen grab, paste it over. Go to library, dink, paste this in. What we see here, if I annotate it, is a really interesting trend. Here we've got our, I'll do it in white so it shows up. Here we've got our zone of stability. This region here, if you have this ratio of neutrons to protons, you're safe. So that's our zone of stability. However, if we look at this region around here, then we have too many neutrons. We've been adding neutrons onto it. So here we have too many neutrons. So nature has a solution to this. We'll put it in this spot here. What it can do is it can take one of those neutrons and it can convert spontaneously into a proton. But nature has to be consistent. And you can't take a 0 charge and turn it into a +1 charge. To make that balance mathematically, you're going to have to add on a negative like that. So nature does. It creates a negative electron. So a neutron decays into a proton and an electron. I'm just going to shade those in. It creates the electron to balance out the positive that's been created. And so inside the isotope, and it's only isotopes this happens, again, we can have our nucleus, and one of the neutrons in there will spontaneously change into a proton. So I'll put my protons in, and my bit big, but hey. And then out will come a tiny little electron, exactly the same kind of electron that we use in chemistry. However, there's one vital difference, and it's its energy levels. This thing has energy levels way and above beyond any electron in a shell. So this thing's emitted with great energy, and that means it has a mass of 1 over 2000. Those with better memories might remember it's 1 over 1842, something like that. But you're never asked about that, so don't worry. It's almost zero. Has a charge of -1, because it's an electron. -1. It has, from penetration, I'm just going to put pen, because I don't want to keep spelling it wrong. It's further. It'll go 20 centimetres in the air, but more importantly, it'll keep going until it hits metal. Usually aluminium, they quote. So this thing can go through your skin and into your body. The other thing is ionisation. Well, it has less charge, and it's smaller than an alpha, so it's moderate. It can knock other electrons off, but it doesn't too often. So that's the second one. The third one, gamma, is far easier. So if we do the third one, it's called gamma. So if we were looking at, you don't have to copy this bit, if we were looking at a hot cup of tea, we would have no problem in imagining that coming off this to get rid of the energy is infrared radiation. And if we have a light bulb, so a classic light bulb with a piece of wire, and there's too much current going through, we have no issue in believing that there's visible light coming off it and infrared light coming off it. So that's a filament inside a light bulb. A bulb, there we go. So what if a nucleus, which has energy many, many times the order of what we're talking here, has too much energy? Well, it has to get rid of it in a form of light, but this form of light has to be extremely energetic. And you may or may not have done the EM spectrum. You possibly did it in year 9 with Mr. Tunstall and Miss Bennett, but the electromagnetic spectrum, if you remember, and we do this in year 11 as a separate module, is radio, microwaves, infrared, visible, that's what you and I are seeing, and it starts with red, orange, yellow, green, blue, indigo, violet. So there's the waves, big wave, small wave. But it carries on. It goes through to the ultraviolet, to the X-ray, and finally to the most energetic type of light, and this is why I'm saying it, to gamma. And as we look at the waves going this way, they get smaller and smaller. Here we're talking kilometres. Here we're talking less than the size of a proton. So as we move this way, we increase energy. And this is why I'm telling you, because if we take a nucleus that has an imbalance of energy, one way to get rid of it, just like the hot cup of tea, is to turn it into an EM wave. And these guys are no good, they're not as strong enough, so they give it off as gamma. So coming off this thing is a high energy gamma wave, like so. Bless me. In terms of mass, charge and the lot, we have a mass. Well, it's a wave, so it has no mass. In terms of charge, no charge. In terms of penetrating ability, it has very high. This thing can pretty much go through anything. And the higher the energy, the more penetrating it is. So there's gamma rays going through you and I right now, and some of the highest energies will go through the Earth and out the other side like we're not there. In terms of ionising, it's the weakest. By far the weakest. So that's gamma. let's go purple for colouring it in. Remember, you can pause this at any point to copy the notes. Right, now there is a nice diagram that links all of this together, and it's this. If we take 3 sources of an alpha, let's make a copy. So imagine we had three radioactive samples of these things, alpha, beta and gamma. Let's get rid of that and that, beta and gamma. So we had 3 radioactive sources coming out. We will draw red for the first. In fact, let's draw the parts first. So we're going to have 3 sheets of things. We're going to have a sheet of paper. We're then going to have a sheet of aluminium foil, a couple of centimetres thick, like so. And then we're going to have a thick block of lead. I'm trying to make them look a little bit metallic. There we go. And we'll label those up. So this is aluminium. And this is lead. Right, so we'll take a red for the first one. So the alpha particles can carry on until they hit the paper. Beta, I'll do in blue, can carry on through, but they get stopped at the aluminium. And the gamma, now the best way to draw the gamma is to draw it as a thick arrow. Some diagrams will show it completely stopping at this point. Others are, I prefer this one. Because it's a probability of it being stopped, there's always a probability that some will get through. And obviously that probability changes with the thickness and the energy of the gamma. But in reality, you find some always gets through. But mostly it's stopped. It's a bit like wearing sunglasses that half the amount of light. If you wear a second pair of sunglasses, well, you don't cut off the other half, you half the half, you get a quarter. And a third pair, and by now you're looking like an idiot. But again, you'll only be at an eighth. And in theory, you can never truly stop it. The numbers will get very small, but you can half and half and half indefinitely. So this is a classic diagram. Now the page number for all of this is, let me just look it up. Hit the wrong button there. Let me see if I can get back to it. Talk amongst yourselves. Is page 44. I'll put that up at the top. Page 44. There'll be some questions to have a go at as well, and I'll try and post a little video extra that encompasses this. As always, any questions, give me an email or put it in the comments. Take care. Bye.